Hey everyone, and welcome to the virtual SQL Beats event for 2020. I'm really glad that the SQL Beats organizers managed to pull this off. This is a really amazing year, and the fact that we are able to run this event in this virtual fashion is really fascinating, I would say, and exciting. So my name is Itzik Ben-Gan. I'm with SolidQ. I spend most of my time teaching about T-SQL and query tuning. In, let's say, normal years, I do it by mostly traveling around the world, visiting both customers, doing public deliveries, and so on. Nowadays, I do the same thing, basically, only I do it, of course, in an online fashion, and I'm really looking forward to start traveling again, meeting people, and seeing places. At any rate, the topic for the session is T-SQL tips and tricks. Basically focusing on backdoors and workarounds for T-SQL elements that are not available. Basically, you want to see some capabilities in the product, but they don't exist. So we'll talk about workarounds for how to achieve those capabilities. So I'll spend basically most of my time during this session using SQL Server Management Studio. So let me switch to it. So we could spend easily the whole week on this topic, going over dozens and dozens of different kind of workarounds and backdoors. But since our session is essentially limited to 50 minutes, we will manage to go over probably maybe 3 or so such capabilities. I'm really hoping that you will enjoy the session so much that you will want to hear much more and attend one of my advanced SQL classes in the future and spend 5 whole days on advanced SQL topics. So let's see. Let's choose a few such missing capabilities. I'll start with one of my favorite tools. Many who know me know that I really love window functions. I use them in so many of my solutions, and among the different window functions, row number is probably the most commonly used. I use it all over the place, all the time. So think with row number, when you compute it, you have to specify ordering. And sometimes, truly, mostly you want to compute row numbers based on some order. But sometimes I do have cases where I need to compute it in no specific order. Okay. So let's go ahead and name our topic row numbers with no specific ordering. Thing is, this is not something that T-SQL allows you to do normally. You cannot just say row number and not specify ordering, but we'll get to this shortly. Once we're done with this, another feature that many people would really love to see, maybe some of you know SQL Server MVP Erland Sommerskog. So he has an open feedback item asking for a function that produces a series of numbers. Postgres, by the way, has such a function called generate series. You provide a low value, a high value, and produces a sequence of integers in this range. Super handy, super useful. You have to come up with your own workaround, basically, if you need such a function in T-SQL. So we'll write a function that generates a series of numbers. All right, good. So this will be our second solution. And then another feature that is missing in T-SQL, those of you who regularly work with table expressions like CTEs, derived tables, and so on, you know probably that when you interact with those table expressions, SQL Server, from an optimization standpoint, unnests, kind of inlines those table expressions and physically interact directly with the underlying objects. In many cases, in the vast majority of the cases, it's actually very convenient for us, and of course, it's for a reason why SQL Server does this. But there could be cases where you want to somehow tell SQL Server, don't unnest. And I'm afraid we don't have something like a hint, what would be very useful, where we could tell it, don't unnest or something like this. So I'll show you a workaround how to achieve this. So let's write here as our third topic, prevent unnesting of table expressions. Okay, so let's start with these three. I'm guessing they will easily fill our 50 minutes, but we'll see how it goes. If we have any time left, which I don't believe we will, I will be more than glad to go over more techniques. So our first backdoor, row numbers with no specific ordering. So let's take as an example a query against one of my sample databases. I will use in my different examples two main sample databases. One is T-SQL v5. If anyone is familiar with the old sample database called Northwind, this is my own sample database that is based on top of Northwind. I like it very much when I want to illustrate logical capabilities of language elements. It's very, very small, the database, very simple, but it's very convenient to illustrate logical capabilities. When I want to discuss performance-related aspects, often I will use a bigger database called Performance v5. So both sample databases are available in my website. So if you go to tsql.solidq.com and then under Resources and then Downloads, you will find TSQL v5 here and also a Performance database available for download. Okay, so let's start with just a basic example of a query computing row numbers against some table. So let's go to the bigger Performance v5 database and then say select, let's say order ID, emp ID, maybe cast ID, order date from orders. Now, without any special computations, let me maybe add another column called filler, which I didn't include in any index, just as an example for a column that has to be pulled from the underlying data row. Here, if I just go ahead and request all rows and a bunch of columns of the table, you will see SQL Server goes ahead and performs a scan of the entire table. Basically, the data currently resides in a clustered index, so you see a clustered index scan. What's interesting to note here is the ordered property of the scan is false, basically telling the storage engine you can go and scan the data in any order that you like. You don't have to return it in index key order. So the storage engine can choose to use an allocation order scan. That's a scan in file order. It is based on IM pages or an index order scan. It's really free to choose any valid capability. Yeah. Now let's go ahead and compute row numbers. Let's say I'll tell it compute row numbers based on, I don't know, a employee ID and then order ID ordering. Yeah. Now in this example, the optimizer will have to choose one of two main options. Yeah. One, if it finds a nice covering index that is keyed by the same elements that we use in the row numbers ordering specification, fantastic. It will request the data ordered true. Basically, for instance, I can show such an example by saying order by order date. Here, our clustered index is based on the order date. So notice, even though the plan seems a little bit similar other than the computation of the row numbers that is happening here, yeah, using the segment operator that handles any partitioning needs of the function. It just tells the next operator when a new partition starts, and sequence project simply assigns the row numbers 1, 2, 3, and so on, starting with 1 at the beginning of the segment. Yeah. But still, looking at the clustered index scan, it looks the same as before, but one critical difference. This time, the ordered property says true, so the storage engine is instructed to return the data ordered by the index key. It's not free to choose between an allocation order scan or an index order scan. So of course, we're giving it less flexibility. Yeah. At any rate, that's when we have a supporting index, we force an index order scan. When we don't, like in the previous example, it's even worse because we have a sort operator involved in the plan. You see, it has no choice but to sort the data by the employee ID and the order ID, as you can see. Yeah. So what's the big issue with sorting? Well, the issue with sorting is, one, it's expensive, and the more rows that you have, the more you pay per row. Yeah, the number of comparisons that the sort algorithm, the SQL Server will use here, using a merge sort algorithm, is n times log n. So the scaling is n log n scaling. With very small numbers of rows, no big deal. With very large number of rows, because you pay more per row, the more rows that you have, doesn't really scale very well. The other issue is, when you think about performance aspects of a query, most people typically think about a performance perspective known as throughput. Yeah, how long does it take the query to complete? Which naturally matters, but there's another performance perspective to take into account. What if we're returning a very large result, but we start filling the user's screen or web page? So there's the performance perspective known as response time that talks about how long does it take the first row to be returned. If we can deliver the first few rows very quickly and we fill up the user's web page, maybe by the time they analyze what they're seeing, we manage to also return the rest of the data before they scroll down. So here, when there's sorting involved, you realize that the sort operator needs to ingest the entire input before it can deliver the first row. And with a very large input, you realize how the response time will be greatly, of course, affected. So yeah, the fact that we have a sort here means it could take some time before the first row is returned, not to speak of the fact that also the throughput of the query is, of course, affected in this negative manner. So the scaling is n log n. This will be the dominant part of the plan in this example. So yeah, if we need to compute row numbers that are based on certain ordering, yeah, we will usually try to create a supporting index if we're able to. Yeah. If we can't, we'll just need to understand the implications on both the throughput and the response time. But sometimes I had this need in a few of my solutions. Sometimes you need to compute row numbers just to produce unique values in the result rows, and it's not like you care in what order you generate those. So if you ever try this, let's go ahead and compute row numbers and not indicate ordering. Try running this, and you will get an error saying an order by is mandatory. Now, maybe you're thinking, and this was my initial thinking when I saw this error for the first time, I said, what if I say order by some constant? Yeah, I tried order by 1, whatever. Thinking, hopefully the optimizer will be smart enough and realize that it's the same value for all rows, so it doesn't really need, to impose an ordering requirement. So it doesn't need a sort or an index order scan if an index is present. At any rate, notice what error we're getting. The error says we're not supporting an index as the ordering element in the order by clause. So what do they mean by this? Just like T-SQL allows you to say order by the ordinal position of an expression from the select list, it thinks that I'm asking it to order by the first expression in the select. So if you say, okay, so what if I provided something else like a string? It won't think that it's an ordinal position clearly. Well, now it will produce a different error saying, well, we don't support constants. Okay. So apparently they need to see an expression. They don't want to see a constant. So if you try something like this, will it be happy? I mean, it's an expression clearly. Well, there is a capability called constant folding that SQL Server has. It's kind of a very early stage of the query processing, even before the full-blown optimization starts, where it sees expressions that are based on constants. Some of those it can collapse to the result constant, and then of course potentially it can improve optimization, we can get better estimates and so on. So SQL Server first collapses this expression to, of course, the constant 2, and now the true optimization starts. So if the optimizer sees the value 2, or it's now even before the optimizer gets into the picture, now there's the issue that SQL Server doesn't allow you to specify an ordinal position, of an expression. So you can see here how we're getting the very same error saying the integer index is not allowed. And same goes for an expression like this, it will first do constant folding, then start the actual processing of the query. And now what it will see is order by the string AB, and we're back to where we cannot use a constant in the ordering expression. Okay. So what else can we do? Well, we need to look for some kind of a technique that will basically prevent the constant folding, if you think about this. So what could prevent the constant folding? And I remind you, constant folding is a very, very early stage of the query processing before they even start evaluating the validity of the query expressions and the full-blown optimization starts. So how about this? What if I tried something that at the beginning looks a little bit bizarre? Yeah, I'll say order by 1 divided by 0. I mean, if this was part of the actual query, like if I place this in my select, yeah, 1 divided by 0 as expression 1 or whatever, and let's just temporarily comment out the row number calculation. Of course, I'm going to get an error that says there's a divide by 0 here, yeah. But going back to our row number computation, the fact that I'm going to get a divide by 0 error in the constant folding phase, basically the evaluation of the relevance of the constant folding here, this part fails, but then we proceed to the actual basically evaluation of the query expressions and the full-blown optimization, of course. And now SQL Server, seeing that we have an expression that basically whatever it generates as a result, it will be the same value for all rows. Well, it realizes that it just doesn't need to sort. It's not like an expression whose result it needs to return. So we have such a bizarre situation where, because the constant folding evaluation failed, and SQL Server knows it's the same value for all rows, so it doesn't go and actually evaluate the expression. It just marks this row number as not requiring any ordering. So the query succeeds oddly. First of all, if I run it, you can see that it actually runs. And if we go ahead and examine the query plan, you will see that it pulls the data from the clustered index, and notice the ordering property. It's ordered false. Yeah. So yeah, it's very, very bizarre. The same thing will happen if you take the maximum possible value in the type, like in an integer, and then add a 1. It's going to fail in the constant folding phase due to overflow, error. But then here in the order by will actually succeed. Do I feel comfortable with this technique? Certainly not. I would not recommend it. I just thought it was kind of curious to show this backdoor, just because it's intriguing, the idea. But in production code, what if in the future they actually do look at the specifics of the expression and try to evaluate in some conditions and suddenly fail? So I prefer other techniques. For instance, some people like to use what you can think of as a runtime constant, that every time the query executes, first is evaluated, but then that value is treated like a constant. Yeah. So it's not exactly like a constant in the sense that, if I specify, let's say, a runtime constant like the speed function, which returns the session ID, every time we execute a query, it first checks what's the current session ID and uses it throughout the query execution. But it doesn't say, wait a minute, your session ID is at the moment 52. I am thinking that you're trying to use it as an index for a column. Yeah, it will not consider it like an actual constant. So this will work. You can see it's running. You can see if we check out the plan, it figures it is the same runtime constant value for all rows. So notice the ordering property is false. Yeah. So anyway, that's a technique. I've seen people using it. I prefer to use another backdoor that also prevents the constant folding, and that's a subquery. Yeah. Whenever you use a subquery, even one that returns a constant. So for instance, if I'll say here, select a 1, the fact that I use a subquery prevents the constant folding. And again, the optimizer is still smart enough to figure, hey, it's the same value for all rows. I don't need to actually sort. One of the reasons that I like this technique so much is because you can personalize it. Yeah. So some people have a favorite number, you know. You will see many people liking 42. You know, you can personalize the message to someone. Yeah, I can send this to the love of my life, Lilach, and say, you know, will you marry me? Well, actually, I can tell you that this week we had our 25th anniversary, so maybe I should send her this query to renew our vows or something. At any rate, you can write anything you like. I mostly like to use a null just because it annoys a lot of people. It's such a controversial element in the database world in general, so heck, why not? So that's what you will see me using in many of my queries whenever I need row numbers in no specific order. Observe again, query is perfectly valid. The plan will show you that we're scanning the data ordered false, so we won't see a sort, and we allow the storage engine to choose between the various strategies that it has: allocation order scan, index order scan, whatever makes sense for the storage engine in terms of isolation level and optimization and so forth. Yeah. So there's our first backdoor. Now let's proceed to the second one. So I mentioned that also in many of my solutions, I like to use a sequence of numbers. I'm sure many of you are using such a tool regularly. Many people just create a table of numbers in the database, fill it with some sequence starting with 1 and going to whatever is the maximum they will ever need. But it could be so convenient to have a function like the Postgres function called generate series that accepts a low value, a high value, and generates the sequence of integers. Let's maybe pull it quickly just so I can show you in the documentation what it looks like. So Postgres generate series. Yeah, and you can see it's a table function. You pass a low boundary point and a high boundary point and say select from, and you can see how it generates a sequence of integers. And then you can convert it to things like date and time values, you know, and so on. It has, you know, many powerful use cases. So how do we handle this? Well, you will see many solutions out there. Some of them not so optimal. So for instance, the most obvious one would be to run a loop that keeps advances by 1 in each iteration and writing the new number into some temporary table. But if you will need a very large number of numbers, like many millions, clearly it's not going to perform too well. Yeah. Another common technique that people kind of intuitively like to use is recursive queries, but recursive queries, they spool the data also physically, and they go through looping for each round of the recursive query, so it's still not a very optimal solution. One of the most optimal techniques that exists in T-SQL to generate generally a large number of numbers before we figure out what to have there, like a series of numbers or whatever, is cross joins. If I'll take a table with, say, 100 rows and do a cross join with another table with 100 rows, I'll get a table with 100 squared, you know, rows. So 10,000 rows will be generated very quickly. Now multiply by another 100, adding a cross join to another instance, and there you go. You have 1,000,000 rows with a cross join between those three tables. So cross joins are extremely fast in generating a large number of rows, basically. So the technique that I like to use for this purpose, very likely we will get input parameters. So let me maybe write it currently as local variables, and soon we will convert it into a table function with input parameters. So we'll pass a low value. Just for the sake of the example, we'll use a 101 as the low boundary point and a high boundary point. Let's set it to say 200. Now, before we start with the numbers themselves, I'll start with a basic table with 2 rows. Yeah, you could have a larger one as your starting point, and it will be a bit more efficient if you have larger tables as your starting point. But just to illustrate the idea, let me start with a table with 2 rows. How do we create a table with 2 rows? Never mind what they have. Well, we'll use what T-SQL calls or SQL calls a table value constructor. Here's a row with only one a column with the value 0, soon we'll name it, and here's yet another row, also with one column value which is 0. Now placing it in parentheses and giving it a name, let's call this table D, and then giving the column a name, let's call it C. For constant, now you're looking at a table with 2 rows, with a column called C. So I can now say select C from this table, and here you go, a table with 2 rows, created from thin air, yeah? Now you realize if I'll do a cross join between 2 instances of this table, I'll get a result set with 4 rows. So this will be my kind of strategy. So what I'll do, I want to work with a series of CTEs, each doing a cross join between 2 instances of the previous CTE. So I'll just name this kind of a table expression level 0, let's say. And here, by the way, you could return the constant column. You could actually create a new constant. Not that it matters. Later on, we're anyway going to produce our own row numbers using the row number function. Yeah. So whatever you return doesn't make any difference at this point. Yeah. So let's go ahead, create a CTE. Let's call it level 0 based on this query. And now have level 1 start the same. Basically, let's just produce a single column made of a constant, but do a cross join between 2 instances of level 0. So level 0, let's name it A, cross join. Level 0, let's call it B, let's say. Yeah. So you realize now level 1 represents 4 rows because a cross join between 2 instances of a level 0. We can actually try it, select whatever from L1 and, select some valid expression, let's try, from L1, and here we go, we have 4 rows. So as I increase the number of CTEs, we can actually compute how many rows we're going to get if each does a cross join between 2 instances of the previous CTE. Yeah. So if we think of the input as the number of levels, let's declare maybe here levels. Let's start with 0 levels, where we have only level 0. Yeah. The formula that will tell you how many rows you will get is 2 to the power of the number of levels. That's your formula. So with 0, you can see we're getting 2 rows. Try 1 level in addition to level 0, and that's 2 squared. Try 2. As you can see, 4 squared. Try 3, that's 16 squared. Try 4, that's 256 squared. And now try 5, that's already 4 billion and something. Very unlikely that you will need more than this, but you know what? If you do, go 6 levels. And I doubt you will need more than 4 billion squared, let's say. At any rate, how do we implement this series? Well, we'll take a separate CTE for each of those levels, and let's go ahead and assign them with increasing numbers and do some copy pasting here. I like the Alt with the highlighting so much. We press the Alt key and then start highlighting rectangles and then do copy pasting like this. For those of you who are not familiar with it, it's so cool and it's so beneficial when you're writing T-SQL code and need to repeat code across a number of rows or copy paste like this. That's a Visual Studio feature, which is very handy. At any rate, now that we go to level 5, we're looking at over 4 billion rows. Now it's time to produce our numbers. So we'll create yet another CTE that we'll think of as our numbers CTE that will go ahead and query L5, which represents over 4 billion rows, but we will use our row number computation that is based on no specific ordering, right? So let's go ahead and apply this computation here. So now, as far as the outer query is concerned, yeah, when we query nums, we're looking at 4 billion and something numbers, yeah? Thing is, of course, we don't need that many numbers. So we want to restrict, but in a way that the optimizer can rely on to apply a short circuit, because if I want only numbers in the range 101 and 200, I don't want to produce 4 billion and then, filter. But that's how top works. Top is requesting rows from its child node, and as soon as the number of rows it's requesting is delivered, it stops making more requests. So it can short circuit. And because we ordered by something meaningless, if we'll say in the top query, order by row num, it will know that it can produce those numbers and stop as soon as it hits the maximum requested and deliver the correct desired result. So let's do this. We'll say select top. Now we need to figure out, how many rows we need to filter. Well, this would be high minus low plus 1, of course. So high minus low plus 1. Think about it. 200 minus 101 is 99, but then the actual number of numbers in the range is, of course, 100. And then we'll say you extract that many ordered by the row num. Yeah, and like I said, the fact that we computed it in this completely non-deterministic manner, the optimizer knows it can simply start producing them and then short circuit as soon as it hits the requested number in the top filter. As for the numbers themselves, we'll need to take the low value, add row num, and of course subtract a 1. So when we take 101, add the first row number 1, we get 102, subtract the 1 to get the actual 101 value as your first value in the series. And let's give a name to this column. Let's say we call it n. Right, so here we go. And let's see what I'm missing. And I just didn't terminate the velocity. All right, so as you can see, we're getting 200 numbers in the range 101 through 200 and produced extremely fast. Yeah. Maybe we'll do a quick performance test. So let's go ahead and maybe encapsulate this in an inline table values function. So create or alter function called dbo.getNums, which accepts the low and high values as inputs, and of course returns a table result as, and then a return clause, and here's our query that generates the numbers. And I'll make a copy for you. As I said, I will share this script file with you as part of the conference materials. So now, whenever we want to go ahead and produce a sequence of integers, all we need to do is just call the function. We'll say select numbers from getNums, and then pass 101, say, until 200 as input. And here we go. Okay. And now let's go and do this. I'll right click some empty area on my screen, go to query options, grid, discard results after execution, so I can ask for a large number of numbers but not print them in the Management Studio grid, because this of course will take a long time. So let's ask for, say, 10,000. See how long it takes. Well, this was nothing. Great. Let's try 100,000. Again, took no time. How about 1 million? Well, under a second. How about 10 million? Let's try. Okay, 4 seconds, not too shabby. And by the way, like I said, you could apply some performance improvements here beyond what you're getting, which is not bad at all, by using table expressions that are not based on 2 rows in the level 0, but rather you could do larger numbers. Like if you go with, say, 10 or even more, you would do fewer cross joins behind the scenes. Here, you get cross joins between 32 pieces. You can actually see this if you go ahead and check out the query plan. you can see after the unpacking of all of those table expressions, you will see that we get basically 32 base tables behind the scenes and the cross joins between them, even though in our case we wrote just 5 levels in addition to 0. Yeah, so by using larger base level 0 with say 10 rows or so, you can get even better performance, but this is not too bad at all. Yeah, so I love this tool. I use it regularly all the time, and it's great to have a workaround for this missing feature like the one that Postgres has. And let's hope that someday T-SQL will actually add such a function in the product. All right, our third workaround or backdoor for missing functionality, that's a capability that I would really love to see available when working with table expressions like CTEs, derived tables, and so on. So what's the story here? The situation is this. Sometimes you need to interact with, say, a CTE and tell SQL Server that you don't want it to do what it normally does, for a reason, by the way, and that's unnesting of the table expression. So let's take an example. Yeah, let's say that we have a CTE called C1 that is based on a query, and then the query does select from, let's say, our orders table, and then let's say where order date is on or after some date. Yeah, 20, let's say 17 January 1st. Yeah, and now I'll go ahead and I'll say I have a second CTE maybe that is based on the following query that does a select from the first CTE, and then maybe add another filter that is a sub-interval of the previous one. Yeah, so if I write here, you know, the order date is on or after January, 1st, 2018, you realize the sub-interval of the first. Yeah. So if I go ahead and do a select from C2, if you go ahead and check out the query plan, you will see, notice how basically what SQL Server did, it's not like it somehow took the data from the first table expression and wrote it into some work table and then queried the work table and took the result and wrote into another work table for the second table expression and then queried the second table. No, SQL Server unnested the table expressions, basically converting the logic to a query that goes straight against the orders table. And also notice how you don't see any mention of all of the predicates, but rather after basically the merging of the intervals, if you will, you can see only one predicate that says all we need to filter really is just those rows where the date is on or after January 1st, 2018. Now you realize that generally this is a very good thing. The fact that it is able to unnest means that we don't pay with unnecessary penalties for persisting intermediate results, for being able to use an index to apply already the sort of processed query filter logic. So in the vast majority of the cases, the fact that we get unnesting happening is actually very beneficial to us, especially from an optimization perspective. But I can tell you that occasionally, here and there, I stumbled into cases where I needed this ability to tell SQL Server here, very specifically here, I do not want you to unnest, and I would really love to have a hint. If I could just say in a query hint, don't unnest, like if I could say here with a no unnesting or something like this, So, as it turns out, there is a very, very simple backdoor or very, very simple workaround here. Apparently, when you use the top filter, but in a meaningful way, that's important. If you ever tried using in an inner query, the combination of top 100%, even with an order by the way, as far as an outer query is concerned, after the nesting of the logic, the optimizer says, wait a minute, when you say top 100%, you mean all rows, so I could actually eliminate this filter. And certainly, if it's only the inner query saying top and order by and the top is 100%, as far as the outer query is concerned, we also don't need to guarantee presentation ordering. Yeah. So there are certain elements that are optimized out, like here. The optimizer detects the contradiction and optimizes the combination out and completely eliminates both the top and the order by and so on. So when I say top is an interesting tool that can help you prevent unnesting, I mean when you use a meaningful top, not when you use a meaningless one like top 100% in an inner query, right? So if top prevents unnesting, how exactly do I use it but still preserve the same meaning that I'm after? Well, if I'll say top 10 and the table could have, thousands of rows or millions of rows, clearly, even if it prevents unnesting, I'm not getting the right thing. So I certainly want to use top in a way that is, for me, meaningless, even if SQL Server doesn't realize this. So what I like to use is simply either a very, very large number or the maximum possible supported number here. Now, top works with a big int as its input. So the maximum possible big int would be 2 raised to the power of 63 and then minus 1. That's the maximum possible integer that you could ever get. Yeah, big integer, I should say. And like I said, top works with a big integer. So if I just copy this number and put it here, now basically, when this query interacts with C1, the optimizer cannot unnest this code. But why? Because if you unnest top queries, you realize that in terms of logical query processing, you could end up causing a change in when a certain step is supposed to be applied. Yeah, generally, top is supposed to happen in logical processing terms well after the where clause. But if here we unnest the query representing C1 and merge this into select top whatever, where order date is greater than or equal to 2018, that's the merged intervals, it's not necessarily going to give you the same meaning like without the unnesting. Yeah. So SQL Server can apply a lot of different transformation rules that reposition, elements like what's called predicate pushdown. Often, SQL Server's optimizer likes to push the predicates in your where clause to a very early stage in optimization because then it can rely on indexing and so on. But it can only apply those kinds of transformations when the meaning is preserved, when the output is going to be the same conceptual table result. Yeah. Here, if SQL Server applied unnesting, in some situations, it could change the meaning, and that's something it cannot do. So essentially, by putting a top here that is meaningful, theoretically, of course, we don't have that many rows, so we don't have anything to worry about, but theoretically, this is supposed to be a meaningful filter. It will certainly prevent the unnesting. Yeah. So we can do it both here and here. Yeah. And then go ahead and examine the query plan. Yeah, and notice curiously how the query plan looks quite different than before. Before, all we had is just, remember, the clustered index seek and the top operator, but now you can see here's one, there was no top operator, of course, there was just the clustered index seek with a predicate that represented the merged intervals. But notice, here's the clustered index seek with only the very first filter predicate. Notice they didn't merge the two predicates into one. Now there's this sort of meaningful top, but what we know that is really meaningless because of the large number. Now comes the second predicate, and again this top, and then we emit the rows to the caller. Yeah. So you can see basically very clearly something that corresponds one-to-one to the boundaries of the table expressions. Yeah. Now you're probably asking yourselves, but wait a minute, this sounds like less optimal when we prevent unnesting, and in the vast majority of the cases you would be completely right. But there are sometimes cases where the unnesting results in strange situations like errors that are not normally supposed to happen if they actually treated each table expression as a separate unit. Sometimes it's more a matter of optimization. Yeah. So Let me quickly direct you to an article where I go into quite a lot of details about all kinds of examples that demonstrate this. And we'll see, we have just a couple of minutes left, so maybe I'll show one of them. But if you go to sqlperformance.com, I have a monthly column that I maintain here. And you look up a series that I wrote recently, I haven't finished it yet, by the way, about fundamentals of table expressions, the fourth part of the series, covering derived tables, optimization considerations. What you see there is just as relevant to all table expressions, by the way, not just derived tables. And here you will see a number of examples where I demonstrate very practical use cases for the prevention of the unnesting. Okay, so let me illustrate one of those, and with this we will conclude. So imagine a query. Let's go switch here to, or maybe I'll take a copy of what I wrote here and put it in the source code file that I will share with you. So I'll write here the top prevents unnesting. Okay, so here we go. We'll query the sales.order details table. Yeah, and as you can see, we have a discount column. Some order lines just don't have the discount, so there's a 0 here. And now imagine if I wanted to do something like this. I wanted to make sure that I'm going to apply some division by the discount, but I don't want to do a division by 0 clearly. And I don't want to take into account whatever is the minimum discount. So even if it's not 0, let's say the minimum discount was 5%, I don't want to take the minimum discount into consideration. So I'll write here that the discount needs to be greater than whatever is the minimum discount in the table. Okay, so that's a simple subquery. Min discount from order details. Okay, so that's pretty straightforward. As you can see now, we don't have any of the 0 discounts involved. But then here's another filter predicate that I need to introduce. Also, 1 divided by the discount has to be, let's say, greater than, let's say, 10. Okay. Now you would think many people, when they write code that looks like this, they say, I made sure that I'm not including the minimum, and if the minimum is 0, clearly I eliminated it, and we can never have negative discounts. So we should never ever get to a point where we try to divide by 0 if we eliminated those rows with a 0, right? But notice what happens when I try running the code. I'm still encountering a divide by 0 error. What just happened? Well, the optimizer does support a short circuit in SQL Server, but it's just that it doesn't guarantee that it will evaluate the expressions in the order that you wrote. Now the optimizer figures this involves interacting with tables and so on, doing a subquery, so it's actually going to be cheaper for it to start evaluating this one. Yeah, and of course, if there's a row with a 0 in the discount, we end up with a divide by 0. So if you're thinking, so maybe I can solve this with a table expression. Yeah, maybe I'll use a CTE. And then handle the filtering of those rows where the discount is greater than the minimum here, and then go ahead and say, okay, now from what remains, I want to filter only the rows from C where, and now the remaining predicate. But remember, we have normally a nesting, and after the nesting, we're back to the original query, and again, an error. How do we solve this? Well, after seeing the technique that I showed earlier, some of you may have guessed, well, we just prevent unnesting by introducing this piece. And here we go. Query is valid and problem is solved. So again, let me go ahead, copy this so you will have this example. But like I said, if you check out my SQL Performance article, you will find additional examples also with optimization. So example preventing errors. All right, good. So a few words just to conclude. Thanks very much for attending the session. I hope you learned something new. I hope you like what you heard. And like I said, if you want a lot more information like this, T-SQL query tuning, I regularly deliver 5-day advanced T-SQL classes. I would love to see you join one day and enjoy the rest of the conference. Thank you. Take care.